All right. I want to hear no. Okay, just heard no. I want to hear Taryn's solution to this problem, because right now, if we add up this column, it sums to 0. And the problem is, it'll sum to 0 for any data set, which means if we use that column as a measure of spread, every data set has 0 spread, in which case that means that it's not worth thought. Nobody's dispersed, which means everybody is that's not helpful, right? Taryn, fix it for us.
I think if you multiply the 82 by the 1, 79 by the -2, 81 by the 0, because that will cancel out like the average, where you have an average on both sides of the average.
Okay, so you weight the data with the distances they are from average. That is an interesting solution. The only problem with that is you're making the lower values not unnecessarily. You're making the lower values skewed more low, the upper values skewed more high, and basically what you're doing in the data set is now going like this with it.
Yeah.
So you're making it you're giving it too much dispersion at that point. That's a friggin' slick way of dealing with it, though. Go ahead, keep going.
It's not there yet. I don't know.
That's okay. It's a neat idea, but unfortunately, I think we bastardized the data set too much.
I was thinking like if you take a look at the extremes, so you could see the more differences between the two.
I am a huge fan. There's a Latin phrase like reductio ad absurdum. Take it to its ridiculous, absurd extreme to see. Unfortunately, when you're trying to measure deviation, you don't want to increase or decrease the deviation without controlling it. How would you then control for it to bring it back, do you think?
I have no idea.
That's okay. I don't expect you to. I don't expect you to. It's a cool way. I'm not saying it's a wrong way, just like I'm not saying Cody's way is a wrong way. Corey, not Cody, Corey. I'm not saying it's a wrong way, I'm just saying it's not the way we do it. So how do we deal with this? You guys dealt with it already in one very logical way. You made the -2 +2. You got it, Alicia. And you made the -1 +1, then you sum the absolute values up. But again, that goes back to that average deviation that nobody uses. So, this is going to be weird. Does anybody know what statisticians actually, how they control for this? This isn't going to make any sense. I apologize. It doesn't. Go ahead, Kale.
Do they square it?
Yes. This is going to seem weird because Taryn's going to be like, dude, you just said I couldn't do it my way. Your way sucks too. So, this is what statisticians do. They square the deviations. Huh? Now, this isn't going to make any sense at first. It doesn't make any sense at first. But it does take care of the negatives. 1 squared is just 1. -2 squared is 4. Sorry, Jason. Jason?
Yes.
Jason, we got the name right. Good. It's okay. This is one of those tiny little bits of math that we're doing. Matter of fact, one of the quiz problems for this week, the primer quiz number 2, involves this calculation on a large set of numbers. It's fun, just to get you practiced in it. 0 squared! Just be 0. -1 squared! +1. 2 squared?
4.
So, 6. Now, the problem with this is, we do blow up the squared deviations. The further we are from average, the more it's going to blow up. So we're kind of in the same boat as Taryn's calculation. But eventually, we are going to take a square root to get rid of the squaring. That's why I said, how are you going to control for that dispersion? What's on your mind, Taryn? What's on your mind right now?
Square root the 4 and stuff, you're going to go back and
Hold that thought. Hold that thought. We're going to do some order of operations before that. So right now, we're going to add that up. We're going to add up. So that's in symbols what it would be. The sum of the squared deviations. That's going to be equal to 10. Some of you are going to take research classes. Some of you already have. And you will see something called sum of squared deviations. It's very often called SS for short. Sum of squares. Anybody seen that in a research journal yet? Sum of squares? No? Okay. Some of you will eventually, especially psych and soc journals. Sum of squares, that's what it is. Sum of squares. It takes all the distances from average, squares those, and adds them up. Okay? It adds them up. I don't particularly think that's a very useful number. Because, well, there's a couple of different reasons. Number one, how would Bert's compare to Ernie's at this point, do you think? How would Bert's compare to Ernie's? Gut feeling at this point. Bigger, smaller, same?
Bigger.
Bigger, huge?
Much bigger.
Much bigger? Okay, good. And tell me why you think it, so I'm hearing a chorus of bigger. Davidson, help me out.
The difference between his scores and the average is bigger, and so when you square that, it's going to get even.
Well said, perfectly said. If you think about how far apart the data are from average inverts, they're much bigger than Ernie's, and then when you square that, it's going to get exponentially bigger. So exactly, so clearly, whatever Bert's number is, it'll be larger than this. Good, thank you. We'll come back to that. We're not going to do Bert's by hand. It gets too tedious. But what we do have to do is average this over all the tests. Just like, there's nothing wrong with what you guys did with the 6 divided by 5 before. That was a good idea. So what we're going to do is, this is the sum of squares. What we have to do now is average that over the number of tests. But this is where it gets a little bit trippy, unfortunately. We're going to take that sum of squares, and we're going to divide it. Now, logic says, what would you divide by? The number of tests you have, right? N. I'm doing, this is going to be in general, N. Statistically, you actually divide by N minus 1. Why? Some of you are nodding like, yes, I've seen this before. If you've never seen it before, you're thinking, what the hell is wrong with you, World? It doesn't make any sense. I agree it doesn't make any sense. It doesn't make any sense at first. It's because you have a sample and not the population. If you had the entire population, you would divide by how many elements you had in the population. But because you only have a sample, you're only dealing with your sample, you don't have to divide by all, you divide by one less. Now, I've got 2 reasons for this. One of them is posted on the enrichment page of your website. There's a reason why you divide by N minus 1 and not N, if you want to get into the mathematics behind it. They're pretty heady, but if you get into the mathematics, it's waiting for you. A better reason is this. If you have a sample, you don't have the whole population, which means you have uncertainty, correct? If you divide by a smaller number, what is that going to have, what effect is that going to have on the entire number if you divide by a smaller one? Is it going to make it bigger or smaller? It's going to make it a little bit larger, isn't it? If you think about 1/4 versus 1/5. Smaller number in the bottom makes for a bigger fraction. So you're going to overestimate the size of the variance, which is a good idea because you don't have the actual population in front of you. That's a bit of a cop-out answer. Corey's like, I don't know if I buy that. Good, you don't have to. Ha! You don't have to, my friend. But when you have a sample standard deviation, there are two good reasons. That's one. The other one's a mathematical one. I don't want to draw it out in class because you'll all hate me in the next 45 minutes if I do that. What's that again?
I will not.
You will not? Then I encourage you, my friend, check out I got a whole mathematical proof for you, waiting for you. I do. It involves a little, well, without saying too much about it. So for us, what does that mean? We've got to take this, which is 10, divided by this, for us, which is 4. 10 divided by 4 is 2.5. Now here's where it gets annoying. 2.5 what?
Average points on test.
Is it points, Corey?
Why is it 5?
Well, 10 divided by 2 would be 5. 10 divided by 4 would be 2.5. Oh, because of the N minus 1. There were 5 tests, minus 1 is 4. This is that annoying point, Corey. Thank you. Why isn't it 5? Logically it should be, yeah? Logically it should be. But mathematically it shouldn't be. And that is not a very good answer. That's why I said I have, Corey, I've got that residual document waiting for you online if you want to get into it more deeply. I wish, the problem with statistics education is sometimes we get the cart in front of the horse. So you actually need a little bit of 244 to satisfactorily answer why that is N minus 1. It's unfortunate. It's unfortunate. So I've got it sitting on that page if you really want to get into it. The quick and easy answer, it's not going to satisfy you, Corey. It's not going to satisfy you. The quick and easy answer is we're going to let technology crunch it because N minus 1 and N are generally so close it doesn't matter. And what I really want you to focus on is that anyway. So it doesn't really matter whether you use N or N minus 1. It's just that statisticians, the research journals, are going to use N minus 1. It's called degrees of freedom. And the more mathematical reason is because you already know what this is, that's 1 degree of freedom checked off, which means you can take it off down here. It's, again, that's a 244 answer, right? You're like, what the hell are you talking about? Degrees of freedom, I want to leave. Don't worry. Just survive this with me and we'll let technology deal with it and we'll interpret the answer in a minute. I promise. I promise. This is one of my least favorite parts, is dragging you through this annoying arithmetic. Please.
So is this how, because like chi-squares have like a...
Chi-squares, yeah.
Chi-squares, yeah.
Absolutely.
Have their own like data set that's
Yep.
ready to
Very,
go.
it's almost identical to this, Scott. Yep,
Okay.
almost identical to this. Yep, absolutely. Go ahead, David.
So Sean, we got 2.5.
Yes!
Try
What?
to get it back to reality. What is this 2.5?
Why do you say reality? Oh, I love that statement. What is 2.5 what? 2.5 what? Not even that. Bigger picture. What's the unit on this?
Points on test.
Is it points on test?
No, it's variation.
Is it points on test? Let us together do a unit analysis track of all this mathematics. What were these? 82, 79, 81, 80, 83. They were points, right? Points. Oh. We subtracted the average. 1 what? 1 what? Negative 2 what?
1
0.
point
Point differences, right? Points different, right? These are still points.
Right.
What's the unit on this? Oh, square points, aren't they? Because we took points and squared them and made squared points.
Point.
Ah, maybe.
Square point.
But my problem is, what the hell is a squared point? What is a squared point? Honey, how'd you do on your test today? Well, 25 or so squared points. So that's 625 points? What is that? The fact of the matter is, we are now in a, oh, I love when you said that, David, back to reality. This is not reality, this is a fiction. That's why I don't like sum of squares. This is squared points. What is a squared point? What is a squared dollar, for that matter? What is a squared IQ score? Any data you'd be looking at, you'd be changing the dimension of it right now. Some of you are like, why is he making such a big deal about this? Is there a difference between inches and square inches? Yes, one is a linear measure and one is an area measure. Exactly. So, how can we fix this? This is squared points.
What would you square root that?
Why don't we just take the square root, Taryn, I promised you a fix. This right here, this thing right here, if you want a name for it, it's actually called something. It's called the sample variance. This thing right here is called the sample variance. Statisticians shorthand it by calling it S squared. They call it S squared. I don't like the sample variance. A lot of people do. I shouldn't say a lot. Some statisticians like it. And there's good reasons in 244 why they like the sample variance. I don't like it. Because you deal with units that don't make any sense. Square points, square dollars, square inches do make sense. But if you're talking about the height of people, that doesn't make any sense because people aren't measured in square inches. They're measured in linear inches. Okay? So if you need the unit to match what reality actually is, you gotta take that and take its square root. And that's where we go over to this board again, and we give the one measure that we actually want to talk about in this class, which is the sample standard deviation.